Welcome back my dear friends, a very good morning, good afternoon and good evening to all of you, and this is the TQM2 class under the NPTEL MOOC series, and I am Raghunandan Sengupta from the IME department IIT Kanpur. So, if you remember, we are in the last week, that means we are going to start the last 5 lectures we will have in the sequence, and if you remember in the 35th lecture, because we are still left with 36, 37, 38, 39, 40. So, in the 35th lecture fag end, we are discussing about multiple linear regression and what is the concept of multiple linear regression, mainly being the parameters should be linear, because that is what you want to estimate, and using that concept of estimation you want to basically put them in the future forecasting or prediction models, and then try to find out how good or bad our models are. Now, if you remember, the simple linear regression was y is equal to alpha plus beta 1 x 1 plus epsilon, where alpha was basically a intuitive feel you can have if you consider the very simple equation we learned in class 10, y is equal to mx plus c. So, alpha and c are similar in nature. So, basically where it cuts the y axis, and the beta 1 is basically the rate of change of y with respect to x 1, and that is basically the marginal rate. So, similarly is there the concept of y is equal to mx plus c, that m value, and this epsilon is basically the error which you have. So, that is the white noise. Then I will come to the later parts of how we do that and how we find out the betas and their beta hats. Hats are the estimated values. Then we have the multiple linear regression model, where rather than having only one x, you have multiple x. So, it is the equation is given as y is equal to beta naught plus or alpha, whatever is said. I am considering beta naught for ease of understanding. So, you basically have beta naught plus beta 1 x 1 plus beta 2 x 2 plus beta 3 x 3 plus dot dot till beta k x k, where k is the number of variables which are used to predict y, plus epsilon, again the white noise. Now, in this case the intuitive field of beta 1, beta 2, beta 3 till beta k it actually means they are the marginal rates of increase of x 1, x 2, x 3 till x k, considering the other variables are constant, in the sense that when I am considering beta 1, we will consider beta x 2 to x k as constant, they are not changing. Hence, we try to find out the partial derivative of the rate of change of y with respect to x 1. Then when we basically go to x 2, then in that case beta 2 is basically the partial derivative or the rate of change of x 2 of y with respect to x 2, keeping x 1, x 3, x 4 till x k as constant, and then we do the modeling part. Now, when you are considering these models, both the simple linear regression and the multiple linear regression, we always consider few very simple assumptions which are intuitive, which may not be absolutely practically possible, but they give you a very good feel of about the model. So, they were basically the x 1 to x k, or even if there was only one x, that is x 1, they are all normally distributed, and hence any convex combination or normal distribution we know it is normal, hence y would also be normal. Point 1. Point number 2, we will consider that the errors are independent of each other. That means, the errors do not change or do not affect the errors of the next period, or one period of t period errors is not affected by t minus 1 period. Number 2, the covariances between this, which means basically the covariances between the errors are 0, variance of the errors is fixed, is sigma square or 1, depending the simplicity on the model. We will consider the errors as a mean value of 0. We will also consider the covariances existing between the error and the x values, x 1 or x 2 or x 3 till x k are all 0. We will also consider the relationship or the covariances existing between the x's are also non-existent, that means they are independent. So, if they are independent, it will, if you basically use the concept of matrix, we will come to the concept that rank of a matrix. So, the rank of the matrix depending on there are n number of observations, that means y 1, y 2, y 3, y 4 till y n, hence corresponding to x 1 they would also be n number of observations, x 2 also they would be n number of observations, till x k also they will be n number of observations, and obviously there will be epsilon 1 till epsilon n and when we basically denote it as a matrix multiplication, so like y is a matrix, capital X is a matrix, beta is a matrix, epsilon is a matrix, we are trying to basically denote it as a matrix multiplication, this multiple linear regression. We will consider the rank of x as k. So, if it is not k, it will mean that one or more than one of the columns or the rows of x's can be expressed as a convex combination of the other rows, which means then it will be difficult to find out the exact values, or the inverse would not exist, and hence trying to find out the values of betas, which are the estimates based on which you are going to predict the future values, would not be possible. Now, whenever you are considering this, you are considering that you want to basically minimize that error with respect to the unknowns, unknowns being beta naught, beta 1, beta 2 till beta k. Now, the question is that how we do that, I have already discussed, but I will still repeat it. It means actually that you want to basically minimize the deviations. Now, the deviations can be of many types, it can be minimum absolute deviations, it can be basically square of the deviations, it can be cube of the deviations, it can be only mod of the deviations, it can be some convex combination of the weighted deviations. But generally we consider is that we consider the square of the deviations, sum them up, find out the errors, total sum of the square of the errors, and then differentiate, partially differentiate. Remember that, because the partial differentiation means that we are going to consider other factors are constant. What are the other factors? That means when we can consider the partial derivation of beta of the sum of the square of the errors with respect to beta 1, we consider beta 2 to beta k as constant. When we partially differentiate the sum of the square of the errors with respect to beta naught, then we consider beta 1 to beta k as constant. When we basically consider the partial derivative of the sum of the squares of the errors with respect to beta I, then we will consider beta naught, beta 1 till beta I minus 1 as constant, plus beta I plus 1 till beta k are also constant. That means, that is why when I mentioned that few minutes back that what is beta naught, what is beta 1, what is beta 2, they are the partial derivative of the rate of change of y with respect to those x's. So, that is what I mean when we say that we are trying to basically partially differentiate that. So, with this we will start this 36th lecture. So, now we want to estimate the parameters, we differentiate, as I mentioned few seconds back, we differentiate with respect to the betas. Now, if you basically do that, you will find out, okay, another thing which I have completely forgot, that I did mention as we were discussing the introduction for the past 5 minutes, that it is a linear equation, in the sense that it is not a square or cube with respect to the values of betas. So, you can have, for example, a multiple linear regression of this form. Say for example, we can have y is equal to beta naught plus beta 1 x 1 plus beta 2 x 2 plus beta 1 2 x 1 x 2. So, in that case you have 4 parameters which you need to estimate, which are beta naught, beta 1, beta 2, beta 1 2, suffix, the 1, 2, 3, 4 whatever I am mentioning are the suffixes. And here in place of x 1 x 2 which are being multiplied, we can consider a new variable as x 3 and consider beta 1 2 as a new estimate we want to find out, which is basically beta 3. But so this is allowed, but what is not allowed is like this equation, which would basically take us into the realm of nonlinear regression, which we are not going to discuss here. It will be y is equal to beta naught plus beta 1 x 1 plus beta 2 x 2 plus beta 3 cube x 3. So, in that case, if when you try to find out and differentiate the sum of the square of the errors with respect to beta 3, it would not give us a term by which we are able to find out the values of beta 3. So, these type of nonlinear regressions are not allowed to be discussed here. Obviously, there are different ways you can tackle those problems, but we are going to avoid that. So, to estimate the parameters, if you differentiate with respect to the betas, so what we have are the set of equations. So, if there are beta naught to beta k, you will basically have such k plus 1 betas, you will have basically k plus 1 equations, partial derivatives put to 0. Based on that, you can find out the values of beta naught hat, beta 1 hat, beta 2 hat till beta k hat. So, this is what we have. So, this is the background which I gave if you differentiate. So, the equation, so you have basically sum of the y values that is basically being equated to. So, obviously, when you are adding up the sum, it will be sum of all the values of x 1 to x k. So, the left hand side, so this has been just written in the reverse direction. So, the first variable on the right hand side of the equation was basically beta naught. So, how many times you are adding beta naught? If you add up all the n values, it will be adding n number of beta naughts, that is why it is n. So, when I go to summation of x 1, so x 1 would basically be x 1 1, x 1 2, x 1 3 till x 1 k, x 1 n, sorry. So, the first one basically denotes the variable number and the second suffixes basically denotes the reading number. So, similarly, for the x 2 it will be x 2 2 1, x 2 2, x 2 3 till x 2 n. For the third one it will be x 3 1 till x 3 n. For the last one it will be x k 1 to x k n. So, this is what they are denoted. This is for the first one. I am just putting a tick mark. So, you basically have a note. This is for the second one. Similarly, you have the third, fourth, fifth, sixth till the kth one. Now, just note down and just highlight, use a different ink color. So, just note down these hats. So, these hats are the estimated value based on which you are trying to minimize the sum of the square of the errors. So, this beta 1 hat is basically the estimated values of beta 1. And obviously, in the long run, as I keep repeating in many of the examples, if you toss a coin 100 times, say for example, you get head 45 times, then you again toss it 100 times, you get heads 55 number of times. If you keep repeating it, then find out the averages of these heads. So, in the first case it will be 45 by 100, second case it will be 55 by 100, third case it may be anything, whatever value. And if you keep finding out the averages of the averages, in the long run for an unbiased coin it will be 0.5. Similarly, if you roll the die and the actual probability of getting a 1, 2, 3, 4, 5, 6 in an unbiased die, it will basically be 1/6. If you keep rolling it, say for example, 200 times you get some number of ones. Again you roll it for 200 number of times, for the second set you will get some other number of ones. If you basically find out the relative frequencies of the chances of the number of ones in the first roll of 200, second roll of 200, third roll of 200, and basically add them up and find out the averages, it in the long run it should come out to be 1/6. So, actually what we mean is that they should be unbiased in the sense that the expected value of the beta j's, j is equal to 1 to k, should be exactly equal to the, so the expected value of the hats, sorry. So, they should be exactly equal to the values of beta j. Similarly, you have beta 2 hat, and similarly for the last one it will be beta k hat. So, the expected value, what I mean is the expected value of beta, no, let me, it is quite difficult to use it. I will use a not a highlighter, but a pen. So, you have basically expected value of beta hat j should be equal to beta j, where for all j is equal to 1 till k. So, you want to basically have this, and this is what would be true for beta naught here, beta 1 here, beta 2 here till beta k. So, all this should be hold. So, when we basically multiply it with now when we differentiate it and then basically do the same thing for beta 1, then beta 2 till beta k, and we have the k equations, because the first one is the total number of equations are k plus 1. So, the first one for beta naught, second for beta 1, third for beta 2, and the k plus 1 for the kth one, beta k. So, the first equation where we have highlighted is basically with respect to beta naught. Similarly, if we have the other equations, obviously you will see that you will be multiplying in the first case as with x 1 1 multiplied by y 1 1 y 1, then it will be x 1 2 multiplied by y 2, then x 1 3 multiplied by y 3, multiply them and sum them up, and then when you basically put it in the equations, you will have the equations as given, which I will denote as, say for example, 2. So, obviously, this is the one. Then you do it for the third equations. So, in third equations, you will basically have, which is not written here, I am just reading, it will be beta naught hat summation of I is equal to 1 to n, because there are n number of readings. It will be x 1 1, and then it will be corresponding to that, it will be x 1 2, then beta 1 2, then you will basically have the summations I is equal to 1 to n, and correspondingly you will basically have the second term, the third term. So, it will be x 1 1 square, then the third term, fourth term till the last term. So, you will basically have the third equation, and the last equation, if you note down, it will be exactly the same, just replace. In the first case, x 1 was being multiplied for the all terms. In the second equation, x 2 was basically multiplied for the all the terms. In the last equation, it will be x k being multiplied for all the terms as it is. So, it will be x 1 k multiplied by beta naught hat, then x 1 k into x 1 I 1. So, I 1 1 1 2 1 3 1 4, so on and so forth. So, the third term would basically be beta naught hat and x I k into x I 2. So, it will be basically, if you sum them up, it will be x the kth variables first term multiplied by the second variables first term, then the kth variable second term multiplied by the second term of the second variable, and it will go on like this. So, you will basically have the k plus 1th equation. So, based on that, you can basically find out the beta naughts to the beta k's. These equations are called the least square normal equations. Why least square? Because you are trying to minimize the sum of the squares, and normal equations because you have normalized them in such a way that you want to find out the beta naught hat till beta k hat. Note that there are p is equal to k plus 1 equations as I have been mentioning, one for each of the unknown regression coefficients. So, how many regression coefficients they are? Beta 1 to beta k for all the x's, and the first term being beta naught. The solutions to the normal equations will be the least square estimate of the regression coefficients, as I mentioned, beta naught hat, beta 1 hat till beta k hat, such that when you find out the nth plus 1 value of y, which is the estimated value of y, which will be given by y hat suffix n plus 1, and you already have the actual value of y n. So, the difference would be the error. So, you write down the error for the nth plus 1, then again you use this beta naught hats, remember the hats are being used, then you find out the y hat for the nth plus 2, write it down, find out the difference between y n plus 2 and y hat n plus 2, which is the error n plus 2. Keep doing it for the third time, that means n plus 3 reading, then you do it for the n plus 4 reading, n plus 5 reading, so on and so forth. Say for example, you collect 100 such errors. Now, technically if errors means n plus 1 error, n plus 2 error, n plus 3 error till the n plus 100 error. Now, if you basically go back to the assumptions which I did mention time and again, then the expected value of the errors in the long run should be 0, which means that if you add up the sum of these errors for the nth plus 1 term, nth plus 2 term till the nth plus 100 term, then it should technically be 0. And if you find out the variance of that, it should also be whatever you assume before starting of the solution. It can be either 1 or sigma square, but obviously this sigma square is not changing with respect to time, which I did mention as an important assumption in multiple linear regression. So, the equation, now if you remember, I did mention that it can be written as a matrix 1. I did not want to write it down there because it would be coming up soon as I thought, and here it is. So, the equation actually can be written as y is equal to, so these are all bolds. So, I am not as shown in the slide, I am not mentioning them. So, they are bold. So, y is equal to x into beta plus epsilon. So, what if you want to basically find out whether it is a matrix and whether the matrix multiplication concept is valid. So, this y is basically of size n cross 1. This epsilon, I am just for the time being skipping x into beta, I will come back within few seconds. Epsilon is of size n cross 1. So, obviously, if you have n cross 1 on the left hand side and n cross on the right hand side also. So, this x into beta should also be of the size n cross 1. Now, in this case we already have beta as, so I am basically writing beta, it is of the size k plus 1, because there are k plus 1 terms beta naught till beta k cross 1, and the value of x obviously would be n cross k plus 1. So, n in cross k plus 1 into k plus 1 cross 1. So, obviously, this and this would vanish. So, obviously, and in the end you have n plus 1 for the terms x into beta also. Now, let us see whether it matches. I have not gone into the details how the matrices look like. So, here this y, well, let me use a different color to highlight. So, this y is n plus 1, yes, it is matching. So, let me put a tick mark with the concept which I mentioned. Let me go to the epsilon first and then come back to x beta. So, this value of epsilon is n cross 1, it is matching, well, good. Now, the value of beta which I mentioned was k plus 1 cross 1. Now, let me see what is there. It is matching. Why? Because there is beta naught is the 0th one or the first one, then you have 1, 2, 3, 4 till k. So, it will be k plus 1. So, this is also matching, and let me put a mark here also. So, this is matching, and when I come to the x matrix, so obviously, I said that it will be n cross k plus 1. So, let me find out how many such rows and columns are there. So, this is the first row, second row, third row till n number rows, how many columns. So, this is the first one, this is the second one, third one, so on and so forth, is the kth plus 1. So, this also matches here. So, all our discussions are in line with our concept which we are basically discussing. In general, y is a n cross 1 vector observations as mentioned few minutes back. N is a n cross p. So, here remember p is the size k plus 1. So, n is a x is a n cross p matrix of the levels of the independent variables as it is rightly so. And in case, oh, by the way, in case if beta naught is not there, the first column which you have for x would vanish. So, obviously, in that case beta would be of size k cross 1 and x would be size of n cross k, because that the first beta naught is not there. So, now continuing the reading. So, beta is a size of p cross 1 which is n k plus 1 cross 1 vectors of regression coefficients, and epsilon is the error of size n cross 1 vectors of random errors, and all obviously all the assumptions which you have been discussing holds. Now, the least square estimates. Now, what do we mean by least square estimates? We have differentiated the sum of the squares with respect to beta naught, put it to 0, then differentiate the sum of the squares with respect to beta 1, put it to 0. So, we have basically k plus 1 equations, we have k plus 1 unknowns, find them, and once we find them, the values of beta naughts or beta 1, beta 2, beta 3 all in the hat values, that because they are estimated values would basically give us the best estimates of the beta values with respect to the concept of trying to minimize the sum of the squares. So, when we find it out, the actual matrix notation is like this. So, this is the matrix notation. So, how do you find out the values of beta hat? Beta hat would be you basically multiply. So, now remember what is the actual size of beta hat. If there is beta naught, it is of size k plus 1 cross 1. So, okay, why I am mentioning that, let me basically give the concept in a more intuitive form. So, it will make sense to you. So, this is of size, if beta naught is there, k plus 1 cross 1. So, let us see whether this balances on the left hand side, on the right hand side. Now, we have already considered the value of x. So, what was x size? X size was n cross k plus 1. Okay. and y, so x transpose would be of size k plus 1 cross n. Now let us go by one. So, for the first term, which is x transpose into x, so x transpose into x would be of size k plus 1 cross n into n cross k plus 1. So, obviously, n is not there, it will be of size k plus 1 cross k plus 1. So, an inverse of that would also be of size k plus 1 cross k plus 1. So, the first step is done. Now, you have again going to multiply with x transpose. So, what is this term? The size of x transpose is k plus 1 cross n. So, k plus 1 cross k plus 1 into k plus 1 cross n would basically be of size k plus 1 cross n. So, this is also taken care. So, this is now k plus 1 cross n. Now, what is y? Y we know is basically of size n plus 1. So, n cross 1. So, obviously, it will be cross n cross 1. So, obviously, in the end you will have the output as k plus 1 cross 1. Now, let us see whether it balances the left hand side. We have already said beta, where I am highlighting with my highlighter, is size k plus 1 cross 1 and it basically matches this one. So, obviously, the dimensions are maintained and the way of we have multiplied the concept of betas are right. To estimate the variance, we consider the sum of the squares of the residuals. As I mentioned that we find out y, whatever the value y, nth plus 1, nth plus 2, nth plus 3, that actual value of y minus the estimated value of y, find out the difference, it can be positive, negative, then square them up, sum of the errors. To estimate the variance, we consider the sum of the square of the residuals as mentioned here. This is the actual value, this is the estimated value, we square them up, sum them up. So, this is a square term which is basically a vector multiplied by its transpose. So, obviously, the size would be of dimension 1 cross 1. It can be shown that the sum of the square of the errors can be written as have been explained. You can find out the sum of the square of the errors and you can find out the sigma squares. Sigma squares would be sum of the square of the errors divided by the degrees of freedom. Now, degrees of freedom I would like to spend 1 minute here. Total number of readings is n. So, for each trying to find out the beta naught, you lose 1 degrees of freedom. So, the total loss of degrees of freedom would be p, which is k plus 1, because you lose 1 degree of freedom to find out beta naught, 1 degree of freedom basically to find out beta 1, so on and so forth. So, the total loss would be k plus 1. So, hence it will be divided by n minus in the bracket k plus 1 or n minus p as you have been denoting. So, with this I will end the 36th lecture and try basically continue with the discussions on the multiple linear regression in more details and basically see that the discussions we had till now, how to find out the sum of the squares, divide by the degrees of freedom, find out the f values, they can be also utilized in the ANOVA table for the regression models and we can pass very nice judgment that whether the variables we are considering or whether they are actually required to find out the overall level of fractional factorial models which are there for the design of experiments and the quality control part. Thank you very much and have a nice day.